Welcome to The Explainer. Today, we're diving into the invisible world that powers pretty much everything in our lives. We're going to peel back the layers on something we use every single second, but almost never really think about: electricity.
I mean, we all know what happens, right? The light comes on. But what is actually going on inside that copper wire? To get it, to really understand electricity, you have to think small, incredibly small. We're talking about the chaotic, beautiful dance of a single electron.
So what's that story look like? Well, it's not a smooth, simple flow, that's for sure. It's really a tale of complete, random chaos being wrangled into controlled order. Let's start by looking inside a simple copper wire, before any power is even flowing through it.
Okay, so picture this. Every single piece of metal, like a copper wire, is just swimming with countless free electrons. But they're not just sitting still waiting for something to happen. No, they're in a constant, frenzied state of motion.
Think of it like a packed room where everyone's just wandering around aimlessly. This random movement is all fueled by thermal energy, just the heat in the wire itself. Electrons are bouncing off each other, zipping in every possible direction. So even with all this frantic movement, there's no overall progress. They're going nowhere fast.
And here's the crucial point. If you could somehow average out the velocity of these billions upon billions of electrons, it would be zero, zilch. For every electron going left, there's another going right, canceling it out. No net movement means no electricity. It's just pure, useless chaos.
So how in the world do we turn that chaos into useful energy? Simple. We introduce a guiding force. Let's see what happens the very moment we connect that wire to a battery. This is where the magic really starts.
The second you apply a voltage, you create an electric field inside that wire. You can think of this field like a gentle but constant slope. And suddenly, all those electrons that were just moving around randomly, they all feel this consistent pull in one direction, from the negative end of the battery to the positive end. And this new directed movement, it's called drift velocity. The random bouncing doesn't stop, not at all. But now between each collision, every single electron gets nudged just a tiny bit forward. And here's the part that'll blow your mind. This drift is incredibly slow. We're talking slower than a snail. So why does the light turn on instantly? Because the electric field, the command that tells them to move, travels at nearly the speed of light. The order is instant, even if the soldiers are slow. This tiny collective shuffle is the electric current. And this perfectly explains what we measure as current. When we talk about 1 ampere, we're really just counting how much charge, how many of these electrons are drifting past a certain point in that wire every single second. But, as you can probably guess, this journey for our little electron is far from a smooth ride. The wire itself presents a constant barrage of obstacles, an opposition to this flow.
Right, so the inside of a wire isn't some empty highway. It's a dense grid of atoms. And as our electrons are getting pushed forward by that electric field, they're constantly crashing into these atoms. It's like a game of cosmic pinball. Each collision slows the electron down and transfers some of its energy. This constant opposition to the flow, that's what we call resistance.
And what's really cool is how simple physical things change this resistance. A longer wire, that's a longer obstacle course, so more resistance. A wider wire is like opening up more lanes on the freeway. Less resistance, it's easier for the charge to flow. And temperature. Higher temperature makes the atoms vibrate like crazy, which means, you guessed it, way more collisions.
This beautiful, elegant relationship is perfectly summed up by Ohm's law. It just says that the voltage, which is the push, is equal to the current, the flow, multiplied by the resistance, the opposition. It's the fundamental rule that governs how all three of these things work together in a circuit.
So we've followed the electron's personal journey. Now, what happens when we zoom out from a single wire to a whole complex circuit? Well, it turns out these flows of electricity follow two very simple, very elegant rules of the road.
These are known as Kirchhoff's laws. The junction rule is just common sense, really. It's like plumbing. Whatever water flows into an intersection of pipes has to flow out. You can't just lose electrons in the corner. And the loop rule is all about energy. If you take a round trip through a city and end up back where you started, your net change in elevation is zero. Same for a circuit. The energy gains from the battery and the energy losses in the components have to perfectly balance out to zero on any complete loop. All right, so our electrons have navigated this whole journey. They've battled collisions, they've followed the rules. But what's the end result of all this controlled chaos? What does it actually do? The electron's journey really has two main outcomes.
First, it delivers the energy that we harness as power. That's the good stuff, the energy that lights our bulbs and runs our phones. But second, those inevitable collisions with the atoms in the wire, they generate friction. And that friction is something we all experience as heat.
And this heat isn't just some random thing, it's totally predictable. Joule's law tells us exactly how much heat is going to be generated. And look closely, it's proportional to the square of the current. That means if you double the current, you don't just double the heat, you quadruple it. That's why your high-powered devices can get really warm really fast.
But we can actually use this heating effect to our advantage. A fuse is just a brilliant piece of engineering. It's a tiny wire designed to be the weakest link in the chain. If the current ever surges to a dangerous level, the fuse heats up so intensely that it just melts, breaking the circuit. It sacrifices itself to save your much more expensive TV or computer from getting fried.
So, there you have it. From a chaotic, microscopic dance comes the power that literally built our modern world. Understanding this fundamental journey, well, it's understanding the bedrock of all technology. It really makes you wonder, if we can create all of this from just a simple, slow drift of electrons, what's next? What will we unlock when we learn how to control the dance itself?